So we are starting the post-processing session now. Uh, I think you are familiar with the singularity image and the MicroSim folder structure by now. So what I'm going to do is I'll start by mounting this singularity image. So I'll launch the GUI first. So this is the GUI we have. So till now you have operated with the in-file generator. So that is the import in file, but you have not operated much with the post-processing tools. I think Nasir yesterday was showing some of the post-processing tools for his simulations. So I'll just continue from there. So here we have the post-processing toolbox, and on the left panel you can see what are the post-processing tools we have. So what we will do is we will first import one in file, existing in file. So for example, we have it. We will start with the dendrite case. Okay. So by now you are familiar with the single dendrite solidification, uh, and also you know how to generate the XMF files from the existing H5 files. So what I am going to show is how to generate VTK from those XMF files, so that you can visualize using the tools on the left side. So first we need to locate the input file, and then since we already have the XMF files, we can just use the path of that. So you might have generated that using the write XDMF, as Professor Ovi showed during his session. So here, yeah, okay, we can continue. Okay, so now here we need to see what is the final time we have for the simulation. So maybe let's have a look. So this is the case directory, output directory we have. And yeah, so here you can see that I already have some GTK files previously generated. Maybe I'll just remove them so that it gets generated again. Oh, sorry. I'll just increase the font size. So you can see all the VTK files are generated, only XMF and H5 files are there in the directory. So now we can move ahead, and yeah, also we need to take a note. What is the final time we have available? I think it is 610,000. Yeah. So this terminal indicates that the conversion is happening, and it is PV-Python in the backend. So that's why we need to we have to add the paraview as well in the singularity image. So it is showing some error warning, but don't worry about that. So we already have the VTK files here. So what we can do is the next thing we can just visualize these VTK files. So we can just click this cross, and then again just we can just go to that directory where this is generated, and then this one has the import. This one imports the VTK, this key. So yeah, the VTK files are already loaded. So we can actually play this series of VTK files. It looks just like ParaView. The way, so this is the single dendrite which is growing. So we have total number of frames, yeah, 61, because it is at the interval of 10,000 time steps. And the next thing we can do is we can do some calculations. For example, yeah, Nasir was showing yesterday how do you generate the velocity at the dendrite tip. So like this, so if we click on this average front velocity, we will uh, get it along across the uh, dendrite tip along the x-axis. So this gives you the dendrite tip velocity. And other than that, we can also specify a line over which you can plot the dendrite velocity. Like, for example, the way we do it in ParaView, I think in the morning, the OpenCL developers were showing it. So velocity over a line, yeah, we can just start from the origin and then let's say it is 1,000 by 1,000 domain. So it needs to be somewhat lesser than your domain size so that it gives you proper result. So this basically we have uh, I plotted it diagonally 0 to 500. So this is how the velocity plot looks. And then also we can plot the dendrite tip radius. So this is how the tip radius evolves with your time steps. So each of these intervals, so there are total 61 files. So each of them are at the 10,000 times. So I think this completes the single dendrite simulation results, the post-processing of the results. And next, we can move on to, let's say, precipitate tools. First, we can do is we can just clear the screen since we are going to import a new WIN file. So this is the post-processing in file, and then we already know how to generate the VTK files from your existing XMF data or H5 data. So we will just import the VTK directly. So yeah, these VTK files are quite big, so they are still loading. Yeah, it is loaded. So again, we can just play it and see how it grows. Yeah, and also it doesn't have the effect of the elastic strain field, right? So that's why this looks circular, like isotropic. So yeah, we can do some operations on this as well, like measuring the area of the precipitates. And yeah, we can also check what are the other fields are there, just like we did in ParaView. This is your alpha phase, and this is your the solid phase, and this is your liquid phase. And then you have this chemical potential of aluminium, and then you have this composition of aluminium. And I think yeah, we can check what would be the total area of this precipitates. So it is calculating. I just clicked on area measurement. Yeah. So you see, these are all calculated. So these are all happening in the backend using a Python code. And yeah, you can see various parameters like uh, uh, so this is basically giving you a field value of this each of the parameters like precipitate area, precipitate radius at certain locations on this. Uh, uh, yeah, yeah, okay, yeah. Each of the precipitates you have this individual values of area and radius, and I mean depending on whether they are slightly ellipsoidal, so you will have major axis and minor axis and aspect ratio. So what we can do is we can plot each of them with time so that we see how they are evolving. You can also export them to CSV by clicking this to CSV so that you can plot it on your own if you want. Or let's say we want to plot the area here, how it is evolving with time. So this is the evolution of area with your time, and then we can also check how to plot this radius. Yeah, this also looks similar because it's just square variation of this radius. And then maybe we can also plot all of them simultaneously like this. So yeah, you can also export this to CSV so in a tabular form. Yeah, I think so yeah, these precipitated tools are complete. I think. Precipitate. Okay. Okay. I click the area measurement. Okay. Precipitate size. Okay. Oh, this is the same thing. Okay. So I just clicked on precipitate count. Let's see what happens. Yeah. So this is how your number of precipitates are changing over the entire time of simulation. Uh, so what is happening here is first they are increasing in size, and then that's how they are rapidly engulfing all of this and combining uh, to lesser number of precipitates. That's how this is falling. So right. If we play it, then you can see at which time step how it looks. So Professor Saswata was discussing earlier. So how this precipitate, how elastic fields affect the precipitates. But yeah, right here we don't have the elasticity field in this particular result. So yeah, I think this completes the post-processing of this precipitate growth results. Then we can move on to this front undercooling. So it is like if you have a directional solidification simulation. So I'll just show it. So these VTK files are getting loaded. Yeah. So yeah, here also you can play it. Let's see. Yeah, these are the. Yeah. Yeah. Right. Yeah. Yeah. So what is happening here is like you can see if we play it like this interface is not it seems like it is oscillating, right? So what we are doing it here is we are just moving the frame, just the interface is moving. So so it's called, so let's say you want to do directional certification in one direction for a long period of time, right? So imagine that you have a box and it keeps rotating, but then if the structure might not have become saturated in the size of the box. Typically, that's what happens. So typically, you go on the size of millimeters, even for even small micrometer size, to get steady. Now, obviously, if you want to track have a simulation domain where the liquid is spanning millimeters,
That's obviously not a issue. In essence, what is happening at the in the physics is nearly at the interface. Far away, the diffusion field is anyway not zero, nothing of it. So there is a way to optimize this where you choose just enough of the simulation box where your composition field decays into the part field liquid sufficiently. On the solid side, remember, typically diffusion is zero, much lesser than the liquid. So not much dynamics happens there. So what we do, we want to take a box of this size, and essentially, as soon as you simulate, have some part of the growth done, you basically cut off the part of the solid that is not necessary anymore, and introduce more fresh liquid from the other side. So essentially, translate the box along with the interface. We are moving along with the interface while it's moving. It's called the moving frame of reference. So in that frame of reference, the interface will not change position. And it is essentially a mechanism which you can turn on in your insights by putting shift is equal to 1. So if you put shift equal to 1, it will essentially give you a simulation condition which is this, and you can measure tell until what part of the box you want to shift. That means you can let the solid grow until some point before you start shifting, and that also is given as a shift J parameter in your insights. Right? It's a mechanism for you to do infinite simulations in a given direction.
Yeah. So, yeah. So we can see. So we know if you specify some temperature gradient or some cooling velocity before running this simulation, so you will be able to plot the temperature as well.
So this simulation, for example, is done with a temperature gradient across the interface, and the temperature gradient is essentially moving at a given rate in a particular rate. So the velocity with which you are giving the translation of the temperature gradient finally will become the velocity of the interface. Okay, that is what.
So this is the temperature at the interface, is it? Huh? Oh, right. Yeah. On the left side now it is the temperature field. Maybe we can just fast forward it and check. Yeah. So yeah, Professor Avik was mentioning about one shift data. So I think that one also you can show. Yeah. So yeah, this is the entire domain at the right side. Right? Yeah, we can just move to the last step. Yeah.
So this is the shifted domain is integrated all into one, right?
Yeah. Right.
Because whatever part is left out, you would like to notice what happened. It's okay left out, but essentially a record of everything that happened. It sticks together into one domain and there, so that we can record the entire structure history. So that's what the shift got integrated does. It will allow you to, although you are doing this finite size of the simulation box, which is moving along, finally you can integrate it all.
And yeah, I think now we can.
Anybody knows what to, if you do a binary alloy, right? It was binary alloy with simple solidus and liquidus defined, and you put a temperature gradient. What is going to be the temperature at the solid at steady state when you're moving with any velocity? Huh? Solidus temperature, why? In principle, it can steady state, but at steady state, only at steady state is the velocity, is the temperature at the solid equal to the solidus. Remember that. So it will go to the CS in the solid, and so CS is equal to the alloy composition. Okay, can somebody come and draw the steady state composition profile? Anybody? For this condition. Write the equation and then you draw. Right, and then the equation. You draw the profile. That's the equation. See the equation. Substitute what is x equal to 0, what is x equal to infinity. And then you get the so you read it, so you read it. Steady state. No, no, K is first. K is first. Only X. Your plotting is on X. What is this? Okay, tell me what is our conclusion. Constant part inside is the solid. Solid. So the solid will evolve to a constant composition and at steady state. What is that composition? C0. And what is the part B composition? C0 except part A is part B composition. KC. Sure. So part B is so this is a essential mass balance problem. Okay. So at steady state, how much composition you take from the part B liquid will be exactly the same composition that it comes out from as the solid. Okay. So that's essentially the which means that T naught by K is a larger value. Exactly. That is the liquid composition in equilibrium. Only the nominal composition is equal to constant. Yes. Then it is otherwise it's not good. Right. So because it's for the small volume, it does add on the okay. This is a check problem. If you want to do a steady state problem, this is something that you take your code, right? You can set up the simulation very precisely in the microstructure network, I mean the software, and do a representative calculation with this, and it should come out. The analytical solution will be reproducible in simulation. Has to. Okay.
So yeah, now we will move on to the next post-processing tool, which is triple point. So here we will count how many triple points will be there in a grain, uh, in a polycrystalline grain. So you can see a grain structure here with a lot of grains, and there are grain boundaries in between. So this is how it evolves. So what we can do is we can just click on this triple point, and yeah, so here we will be able to know the coordinates of each of these triple points in the grain boundaries in between the grains, and how these are changing. So you can save it to some CSV and then plot the evolution of it. Yeah, I think that's all. Grain boundaries. Oh, so yeah, so next there will be another post-processing tool that is in development. So I think that will be integrated to this post-processing tool soon. So Anshika will present this. Oh, yeah. Oh, 2.4 positions. Yeah. What's going on? What was it? Oh,
So, uh, this is an interesting measure of microstructures, which is called a spatial correlation. Okay? Spatial correlation is essentially trying to see that microstructure is say over there, and it can essentially be essentially telling you to take one point on the image and take any vector corresponding to another point. Right? This is the vector in the image. How many times or what is the probability of this particular vector of this size to be there in the microstructure? I think the start point is this. It starts in one color and ends in another color. Okay, with this length. How many times does it emerge in the microstructure? What is the probability of that vector? And you do it for all possible vectors. Okay, so that is what that color representation shows you. Essentially, it is a way to, if there is a texture in the microstructure or some bias in the microstructure, it will be visually captured with that spatial correlation. It's a two-point spatial correlation. We can have higher order correlation, 3 point, 4 point, and point, and so on, depending on the requirement to get captured. No, I mean, in this summer, in this so you may want to know about the 5 MKS, there is a library by Surya College in Georgia Tech, Surya College. We have developed a Python library called PyMKS. You will actually such correlations will be obtained. Okay. But this is absolutely
But this is Python.
extensive work available on the platform. What are the accesses and not like that? It is the same election. No, I mean, if we are talking vectors and so essentially, it is telling that the 0, 0 vector over there has some intensity. Okay, it is essentially converting this guy into a grayscale, and the point at the center is something that is related to volume vector. So the color intensity will reflect the volume vector. Okay, so there are some measures that come out immediately, but all of it is not so easy to correlate. It gives you essentially another space to represent your microstructure. Essentially, the principal.
Yes.
So you want to take measures out of the microstructure, you can essentially compute what are known as principal components. And these principal components are what are, if you were to do the statistics like that, and take it to what is known as the orthogonal base set of this. And from that, you find out these particular variations in the microstructure which are having the maximum value. Okay? This is what would come out. Okay? The first three correlations or first three measures which are having the maximum variation have this value. So what from this what you see is PC1, for example, which is the blue one is changing, whereas PC2 and PC3 are constant with time approximate. The other ones are essentially having finite variations about an average value, whereas PC1 is changing with time. Essentially, which means the average grain size is changing with time, which is what would happen in the grain growth problem. That is what is getting captured. Right? Other features, they have some physical meaning. The association with the physical part of the microstructure is not too trivial. But what it shows you that some measures of the microstructure can be directly quoted. So the use of these principal correlations are sometimes in machine learning. So for example, I want to associate this grain structure with some property, which I know is varying. Okay? What I will use is I will hook up a law or a mathematical modeling using this principal component. That mathematical model can be as diverse as it can be. And the coefficients of those models can be fitted with the property that I am wanting to measure, and you have a machine learned model. Then what you have? You essentially can have a grain growth model. A grain growth model will evolve. These PC components will be a function of time, but you have a structure property model from MI. If you have a then process structure property correlation in one go. Okay, so that is essentially the broad future overlook of the utilization of these type of measures that you can get out of these microstructures and the final structures and property correlations that you can derive. Right? So that's in statistical space it becomes a little bit tricky. Essentially extracting features of the microstructure.
So let's say if you are doing homogeneous, the grains are elongated in one particular.
Yeah,
so PC map will be
different. So PC map will essentially be a numerical map like this. But the spatial correlation map will show you an elongation of one vector. Whichever direction is elongated, it will show you along that vectorial direction maximum coordinate.
So is it like we're converting this grain to a graph and then getting an FFT of this graph?
It's similar to an FFT, but FFT, remember, is a reciprocal space. This is representation of the same real space itself.
Okay. The secret we are counting for
Yes.
this.
Yes.
So if you rotate this, does the conversion change? Maybe not. But it is real space and
Real space will change. In real space it will. Okay. So in the 2-point spatial rotation that you have here, any change that you do in the rotation will flip the plot. So you have a different spatial rotation, although not physically. Okay.
so if you are doing case revision modeling, you do sine wave changing. But as a human, the field that is still related. So you see that our brain has higher computing than the case revision. Right?
surface area plots are also there.
Yeah. So
Not in this one. The other one, dendrite and everything.
dendrite.
Okay. Surface volume phase fraction. All of that. There's a huge data set. So sharing the data is
So yeah, so I'm just sharing that same dendrite growth simulation results again, so that we can show some other capabilities of it. So yeah, phase fraction. Yeah. So for example, we can calculate the phase fraction from this simulation.
So it's a linear growth of the phase fraction. Okay. Take the volume.
Yeah. So yeah, we can also check the volume. Yeah, this also grows linearly.
What about the surface area?
Yeah.
You see, surface area is
Yeah. So this is somewhat parabolic.
okay, so this is not trivial. So this some sort of theory of how diffusion feeds into the density growth. So the volume is linear because it is essentially diffusion control group. So your volume will be proportional to time. So it comes up. Whereas surface area portioning is not linear. Surface area, the RQ is function of time. So that will come out say as linear versus right? But this is not linear. Okay. So yeah, they have a constant factor. I think this is that power of P is different. This is P power 0.5 or P power 0.7. P power 0.5 actually, what it would be like. So, but this is something interesting I wanted to point out. The surface and the volume grow differently on a delta. I think that
Yeah. So, yeah. Now yeah, we can move on to the grain size distribution.
so in terms of people who want to contribute, right? This tool making is something I am always interested in having people contributing because there are different body sets you can easily do it. There are typically Python codes which interact with the data, and the way of interaction with the data is standard. You have a way to extract the data from the simulation, and then it's available for you to query. All right. So there are several ideas we have at different points of time. So if at any point anybody of you are interested in developing,
You want to shift to
you
it?
can
You can stay.
write to us.
So following to the other tools, we have a new tool, grain size variation. So when you click on this grain size variation tool, you will be having a different formats. So if you have EBSD scan images, you will be able to see the microstructure as well as you will be able to plot 2D or in the 3D view. So I'll show you from one example of by importing a Dream 3D file. So I have generated a data from Dream 3D. This is an Dream 3D open source software where you will be having a different workflows and you can generate pipelines like using pipelines you can generate the data and here there's a file will be
How many of you have heard about Green No, more than 2 months. So MPD is essentially an open source way to view orientation pipelines. Okay. The .dh files or files that come from PSP software. Typically, you use PSL software, which is a commercial software to anything post process the data that comes out of the ABSD machine, right? Real basically is a open source machine. You can do one more. You can not just visualize them, you can operate on them, extract all the information that comes out of digital orientation. That's typical DFL software. You can also generate microstructures corresponding to what you do. So it's a powerful software, so open source software. You might want to get it.
So I'll show example, like you are having a Dream 3D file. So you just open it here. And if you click on plot microstructure, you will be able to see this microstructure type of figure. So this is also called as EBSD scan images. You can, like metallurgy people do from experimental things. Here you will be computationally generate them. So plot 2D. So the grain, the microstructure you have seen there. I guess. So it's taking time. Yeah. So here you will get the plot. So the microstructure you have seen. So there are grains. So the number of grains you can count by the area, like what the individual like or separate grains you are having. You can check the area according to this graph. So this is the graph. Like suppose you are having the histogram plot. This is the histogram plot. So 0 to some area like 200 or 150, you can check that 11 or 10 graphs, 10 grain number of grains are here. So you can zoom it, or you can just see like 11 grains are in this area, 150 approx.
So essentially, a grain size is what? So typically, if you have triple grains, principal question we would like to know is how many times the grains, what is the frequency we use here on that. So grain size is something that is very essential. So this has to be integrated. So presently what is showing is box or doing any data. The idea is to essentially have it with any sort of image or any sort of input, image or raw data.
Yeah, as we having different formats. So you know about the .tiff file, .vtk, .bmt. So that BMT is my binary microstructure tool. So also TIFF, there are another softwares also there. There's Matbox where you can generate TIFF images or like kind of EBSD scan images. So these, so you can directly import the data from here. Simple like image, you can even use the .jpg file and can directly generate the data in histoplot. Okay, thank you.
All right, so that essentially gives you a broad overview of the possible input boxes. There are other things we will be adding. You've seen some of those tabs which are not yet populated. So, for example, triple point angles and so on, which will be going along as we develop. Yes. So with that, I think I think the other exercise you have already done some simulations have please use them. And then because you have just heard about all of these things, so it's a good idea that you already have some Excel files, you already need some simulations. So just open this post processing tool and try out all of the options. For example, volume fraction, phase fraction, surface area, all of that will come up. Okay.
Stop sharing.
I definitely I can find I will see it ready. And
Share the screen also then.
Yeah.
Shall I watch?
Yeah. Everyone has opened the post-processing tool. Any questions here? Oh, right. Yeah. I mean, in the sense, this is readable. Others, I think, because of screen resolution.
It is.
So first you have to load the in file of that particular simulation which you want to convert to VTK and then visualize. Okay. So you have to make sure that you are using the correct in file. Otherwise, this tool will not work properly.
Android you want to open to it because they have level Android data. So yeah, this is the select and you will file it up. Next you want to.
So we are opening a dendrite simulation and we'll convert it into XMF to VTK. XMF data you already have, right? So you just go to a folder which already has H5 and XMF files. So load that particular in file. Then you have to go to H5 to VTK.
Android. Get data. Sorry. Click on in file. Oh, so that is the in file, right? So yeah, there you need to.
So again, you have to load the in file here. Then because we already have XMF file, so click on XMF and then do locate. Then again go to that folder. So here it will show a list of XMF files. So select the first file, the 0th XMF file. Okay. So this is the 0th file. So I'll select that. Then you have to mention the start time 0. And then step size, whatever is the step size that you had used for the simulation, the step size at which you are writing the files. That was 10,000. Okay. So it's not necessary, but you can specify that.
Something like 10,000 or just put to. Yeah, in time you say what is your end time? You need to specify corresponding to that. You say that.
So you go to your folder and just check what is the end time, what is the last H5 or XMF file that you have, what is the time corresponding to that file. Okay. Maybe 100,000, 20,000, you are doing 20,000 iterations.
Yeah. So
For the case that we have here, we have the files up to 6,10,000. You might have 20,000, 40,000. Just check, okay, and enter that number here. Then this is an optional thing. If you want to, by default, it will generate the VTK files in the same folder if you don't specify anything here. So we'll leave it as it is, and then click on convert.
So for some people, it might not show up anything in this terminal. For some people, it might show some warnings. Everything is fine. Are you able to follow it? Backside, Ajit.
They are able to generate, right?
So any simulation that you've already done, open the folder and try to it.
Let's just make it open for some time.
So once it is loaded, you can just close this window, and then all of this left-hand side tab options will highlight. Then you can try out those options. If you have any questions, you can get back to us.